Like, where did data science start? Let's maybe look quickly at the history.
Okay.
Its roots, they actually go way back to the beginnings of statistics and computer science. Those were the foundations.
Yeah, and it's interesting, the term data science itself isn't brand new. Someone named Peter Narr used it way back in 1974. Yeah, basically as another name for computer science at the time. And then later, in 1997, Jeff Wu actually suggested we should just rename the whole field of statistics to data science.
See, so the idea's been bubbling under for a while, but the formal recognition, that really kicked off around 2001.
Right, with William S. Cleveland.
Yeah, he essentially said, hold on, this is actually its own distinct field. He saw that with the growing amount and especially the complexity of data, we needed a more specialized set of skills, something that went beyond just traditional statistics or, basic programming.
Looking at the bigger picture, Cleveland's argument was really a key moment. It acknowledged that getting meaningful knowledge from modern data required this specific synergy of skills that hadn't really been formally recognized together before.
And then came the real game changer.
Yeah.
Big data. Early 21st century.
Ah, yes. The big data explosion.
Suddenly, we weren't just dealing with more data, but these massive, incredibly complex collections of information that weren't organized neatly at all.
Oh.
Unstructured stuff.
Right. Text, social media feeds, sensor data.
Exactly. And the traditional methods, they just couldn't handle it. Let's start early then. What about high school students? How should they prepare if they're interested in this?
Yeah, building that strong academic foundation early on is just critical. The absolute core subjects are computer science, mathematics, and statistics. And it's not just about passing the classes. These subjects teach the fundamental logic, the analytical thinking that underpins everything in data science.
Which specific math topics are most important, would you say?
Linear algebra, calculus, and definitely probability and statistics. That's the theoretical bedrock. Understanding those helps you understand how the algorithms actually work later on. In computer science, getting some programming experience, especially with Python if possible, is a huge advantage. But honestly, even a solid foundation in programming principles using another language, like Java and AP Comp Sci, is great. Python syntax is relatively easy to pick up once you have those fundamentals. And high school is also a great time to start playing with data science concepts directly. Learning about collecting data, cleaning it up, analyzing it, visualizing it, maybe trying small projects, analyzing some public data sets. Just cultivating that critical thinking and data literacy early makes a big difference.
Okay, what about university? Are degrees still the main path? And how necessary are advanced degrees like masters or PhDs?
Formal education is definitely still a primary route, yeah. And your sources strongly suggest an increasing emphasis on advanced degrees, especially for those more specialized roles or leadership positions. For a general data science role, a bachelor's in something quantitative data science, CS, math, stats, engineering is often the entry point.
Okay, but what if someone doesn't have that traditional academic background? Or maybe they're looking to switch careers entirely. Are there other solid options to get the needed skills?
Oh, absolutely. This is where things like industry certifications and all the online learning platforms become incredibly valuable. They offer structured, flexible, and often very accessible routes to getting specific job-ready skills. This is particularly good news for career changers or people needing to upskill effectively.
Tell me more about certifications. How much do they actually help?
They can help a lot. Industry certifications act as a clear signal to employers that you possess specific, validated skills and knowledge they're looking for. Earning a respected certification, say from AWS or Google Cloud or Microsoft Azure, can really boost your marketability because it proves hands-on competence with their platforms. For machine learning engineers, cloud provider certs focused on ML are strong options, though some require prior experience. Certs from companies like Databricks also validate skills in specific ML tools and workflows. For data engineers, again, cloud platform certifications are really popular. Microsoft Azure, Google Cloud, AWS all have them. Your sources also mention some beginner-friendly options, like a metadatabase engineer certificate or programs like IBM's data engineering certificate that are specifically designed for career changers, sometimes with no prior experience needed.
precise set of steps.
What?
Finite steps, step-by-step instructions, basically, designed to solve a very specific problem or, perform a task.
Like recipe.
Exactly like a recipe. Think of it as the conceptual blueprint. It's the logical sequence, and it's totally abstract, language agnostic.
Yeah.
It's the pure idea behind the solution before it gets turned into code or anything runnable.
Right, the pure idea. And this blueprint thinking, it's not just for computers, is it? This precise sequential problem solving. It seems pretty fundamental to how we think, too.
Oh, completely. It has defining characteristics, right? Each step has to be unambiguous.
Right.
It needs to finish. That's the finiteness. It takes something in, an input, does something, and gives something back, an output.
And it needs to be general enough to work on different inputs, not just one specific case.
Yeah.
And effective, like actually doable.
Precisely. Think about tying your shoes. That sequence of steps, that's an algorithm. Or a navigation app, finding the best route. Algorithmic thinking is really a core human skill. Pretty much every algorithm, no matter how simple or complex, follows this universal pattern. Input, process, output, IPO. You give it data, that's the input.
Right.
It performs a set of instructions on that data, that's the process.
The steps.
The steps, exactly. And then it produces a result.
Simple enough. But how does it handle complexity, choices, repetition?
Well, that's where control flow comes in.
Yeah.
There are basically three fundamental structures. You've got sequential execution, just doing tasks one after another in order.
Okay.
The conditional logic, the if this, then do that, otherwise do something else. That lets it make decisions.
Makes sense.
And finally, iterative structures, loops. Repeating steps over and over, maybe until a condition is met. That's incredibly powerful for processing lots of data or refining results.
And that processing power, especially with iteration, must be why algorithms are so crucial in data science, right? With the sheer amount of data we have now.
Indispensable. Absolutely critical. Algorithms automate these incredibly complex processes on massive data sets, things humans just couldn't do manually, not at that scale or speed. They turn raw, messy data into actual, actionable insights. And they do it with high precision. Consistency.
And they enable predictions, right?
Exactly. Predictive capabilities are huge. They let us see patterns, make forecasts. Without algorithms, big data is mostly just noise. Okay, given how advanced this sounds, what kind of technical skills do AI engineers need?
Strong programming is a given. Python, yes. But often Java and C++ too, especially when performance is critical. They need deep expertise in a range of advanced ML and deep learning algorithms. Frameworks like TensorFlow and PyTorch are standard, of course, but what often sets them apart is expertise in specific AI domains. And the tools used there, like, say, Hugging Face or LangChain for NLP, or specialized computer vision libraries, and experience with large language models, OpenAI's models, Llama, etc., that's becoming super important. Plus, managing the whole development and production infrastructure, including cloud deployment at scale.
And outside the core tech skills.
Well, strong problem solving is crucial for tackling these novel AI challenges. And like the other roles, excellent communication is vital for working across teams and explaining what these complex AI systems can actually do.
How does the career path look?
Starts junior, then AI engineer, maybe AI team lead, or up to AI director. But people might also specialize further, becoming a deep learning engineer or a computer vision engineer, or move into designing the overall systems as an AI architect. Just fueled by how rapidly AI is being adopted across pretty much every industry, tech, finance, healthcare, you name it. A really critical insight from your sources is this. The demand for AI experts, particularly in those cutting-edge areas like generative AI or deep learning, is currently outpacing the supply of qualified people.
Explainable AI, XAI, what's the goal there?
The goal is to make the decisions and predictions made by complex machine learning models, especially black box models like deep neural networks, understandable to humans. Why did the model approve this loan but deny that one? Why did it make this specific medical diagnosis suggestion?
Right, because if you don't know why, it's hard to trust it or fix it if it's wrong.
Precisely. XAI techniques aim to provide interpretable explanations for model outputs. This helps data scientists improve their models, helps organizations meet regulatory requirements, especially in areas like finance and healthcare, and crucially helps build trust with users and stakeholders. It allows you to trace errors, identify potential biases.
Which leads nicely into responsible AI. That sounds broader.
It is broader. Responsible AI is more of a governance framework or methodology for developing, deploying, and managing AI systems in a way that aligns with ethical principles and societal values. It encompasses fairness, accountability, transparency, privacy, security, reliability. Basically, ensuring AI systems behave ethically and benefit humanity.
So XAI is part of responsible AI.
You could see XAI as a key technical enabler for achieving aspects of responsible AI, particularly transparency and accountability. There's growing concern that AI adoption is outpacing the implementation of proper governance structures. Responsible AI aims to close that gap, making ethical considerations mandatory, not optional.
Are these just nice to haves, or are they becoming essential?
Increasingly essential. Regulatory pressure is growing globally. And beyond compliance, ensuring fairness and mitigating bias through XAI and responsible AI practices can actually be a catalyst for innovation.
Now let's talk machine learning, or ML. This is where things get really interesting for a lot of people.
This is where the learning part comes in.
We're talking about algorithms here, basically. Sets of computer instructions, but algorithms that can learn from data. They figure out patterns and make decisions without being explicitly programmed for every single scenario.
And the key is they improve over time. The more data they process, generally, the better they become at whatever task they're designed for.
That ability to learn, to adapt based on new data, that's what makes ML so powerful, right?
Hugely powerful. It allows us to automate the process of finding complex patterns, significantly improve our ability to predict future outcomes, and even things like cleaning and organizing messy data more effectively.
And there are different ways these algorithms learn, aren't there?
That's right. There are several main paradigms. You've got supervised learning.
Okay, what's that?
That's where you train the algorithm using data that's already been labeled with the correct answer. So, like your example earlier, you feed it thousands of pictures labeled cat and thousands labeled dog. And it learns the features that distinguish cats from dogs based on those labels.
Okay, so it has a supervisor telling it the right answers during training. Makes sense.
Exactly. Then you have unsupervised learning. Here, the data is unlabeled.
So, no answers provided.
Nope. The algorithm has to find structure or patterns in the data all by itself. A common example is clustering, grouping similar data points together without knowing beforehand what the groups represent. Or think about spam filters in your email.
Okay. How does that work?
Well, they often use unsupervised learning to identify emails that share common characteristics typically found in spam, even without a giant pre-labeled list of every possible spam message. It spots the patterns.
Gotcha. Okay, supervised, unsupervised, any others?
There's semi-supervised learning, which, as the name suggests, uses a mix of labeled and unlabeled data. Often you have a little bit of labeled data and a lot of unlabeled data, and it tries to leverage both.
Okay.
And then there's reinforcement learning. This one's a bit different. The system learns through trial and error, essentially. It takes actions in an environment, and it receives rewards or penalties based on those actions.
Like training a dog with treats.
Yeah.
Or maybe like how an AI learns to play a complex video game.
Precisely. It learns strategies over time that maximize its cumulative reward. Very powerful for things like robotics, game playing, optimization problems.
Wow. So supervised, unsupervised, semi-supervised, reinforcement. Quite a range.
It's interesting to consider how this variety of learning approaches means machine learning can be applied to many different kinds of data and solve a vast array of problems.
And ML is behind so much stuff we use every single day, often without even realizing it.
An embedding is basically a coordinate, a point on this huge multidimensional meaning map.
A meaning map, okay.
Yeah. And on this map, things that are similar in the real world, their points, their vectors are close together. So king and queen might be neighbors.
But king and, say, apple would be miles apart.
Precisely. Worlds apart. The distance itself represents semantic similarity, or lack thereof.
And this isn't just a nice idea, right? This map is something machines can actually work with.
Absolutely. By turning concepts into these numerical vectors, machines can use tools like, linear algebra to perform calculations. It lets them process all that messy, unstructured stuff, text, images, even audio.
So it's like giving them a mathematical language to understand our kind of fuzzy, complex world.
You got it. And it's crucial because, well, the older methods just couldn't do this.
We've seen how this quite elegant idea, turning complex stuff into numbers on a map, has become fundamental to AI.
Yeah, from search to recommendations, they're everywhere, powering so much. This conversion to a universal numerical language is key.
But looking ahead, and this is maybe something for you, our listener, to think about, is this enough? Is a single fixed-length vector, however sophisticated, ultimately going to be limited? Can it really capture everything needed for truly deep reasoning or, say, complex instruction following in AI?
That's the million-dollar question, isn't it?
A really key technique behind this is something called embeddings.
Embeddings.
Yeah, think of it like create a giant map in many dimensions. Every item, every song, movie, article, and even you, the user, gets placed as a point on this map.
Okay.
And the key is that distance on this map represents similarity. Things that are conceptually close are placed near each other. This lets the system blend all these different signals, your tastes, other people's tastes, items characteristics really effectively.
That makes sense. It's like a similarity map. Let's make this concrete. Spotify, for example. They build this really detailed taste profile for you. Right?
I do. And they even talk about having multiple U vectors. Like maybe you have a different taste profile for your morning commute versus your evening wind down.
Huh. My late night you definitely has different tastes. Probably just ambient sounds.
Right. And Spotify also digs deep into the audio itself, not just genre tags, which helps with brand new music. And they use this technique, contextual bandits, to constantly test. Should we play a favorite or try something new? It's like a little experiment.
Very smart. And Netflix. They go super niche with genres, don't they?
Oh yeah. Thousands of micro-genres. Things like emotional independent crime movies. Really specific stuff to match just what you might be in the mood for. And get this, they even personalize the thumbnail image for the same show.
You mean the little picture you click on?
Yep. They might show you a picture emphasizing the action elements if you like action, or one highlighting the romance if that's more your thing, for the exact same movie.
That's wild. And TikTok, of course, its For You page is legendary for how quickly it learns.
It's incredibly agile. It takes your feedback, a quick swipe, a longer linger, and incorporates it almost instantly. It's designed to keep up with concept drift, which is just how fast our tastes can change.
But what about, the human element in all this? Is it purely algorithms?
Not always. Apple Music's an interesting case. They actually employ over 1,000 human curators around the world.
1,000 people?
Yeah, to work alongside the algorithms. The idea is to help mitigate biases the algorithms might develop and to promote more diverse content.
That's a different approach. Okay, so this personalization, it feels pretty seamless. But what's underneath it all? What's the actual data they're building this on?
Well, it always starts with data. Lots and lots of data. The early systems, way back, like one called Grundy in '79, they needed you to tell them what you liked. Explicit feedback.
Like rating things.
Exactly. But today, Spotify, YouTube, Netflix, they mostly rely on implicit signals. It's about what you do.
Like what specifically?
Well, your play counts, obviously. If you skip something really fast, especially like before 30 seconds, that's a signal.
Huh.
How long you watch or listen, what you click on, what you share. I mean, even where your mouse moves on the screen sometimes.
No way, really. Mouse movements.
It can be part of the mix. It makes it easier for you, the user, because you don't have to constantly rate things. But it does mean they're inferring your tastes, not asking directly.
That's fascinating. Okay, so they have all this implicit data, clicks, skips, watch time. How do they turn that into, hey, you should watch this next? What's the logic?
So there are sort of two main strategies, big picture-wise. The first is called content-based filtering.
Okay.
This one suggests things that are similar in content to what you've already liked. You listen to a lot of pop music, it gives you more pop music.
Makes sense.
And it's pretty good for new users, right?
Yeah.
Because it doesn't need info about what other people are doing, but it can create a bit of a bubble. Over-specialization, they call it.
Right, like an echo chamber. You only see more of the same stuff and maybe miss out on discovering something totally different.
Precisely. And that leads us to the second main approach, collaborative filtering. This one looks at other users.
How so?
It finds people who seem similar to you, they've liked and disliked similar things. Then, if those similar people like something that you haven't seen yet, it recommends it to you.
Ah, so that's where the unexpected, maybe serendipitous recommendations come from.
Exactly. That's the strength. But it has its own challenge, the cold start problem. If you're a brand new user or there's a brand new movie with no interactions yet,
The system doesn't know who's similar or what to suggest.
right, it needs that interaction data to work well.
So this is where it gets really interesting, I think.